Okay, so thank you for coming this afternoon, just for this. I thought I would skip my own talk, but then I thought it was rude. Before we start seriously, I would like to thank IPAM and Christian and Dima and everybody, because I think it has been a good program, very good program, and I see things happening, and I'm very, very happy for that. You two wait to say thank you after you see my talk, because you might change your mind about being a good program. Also, since it's the only talk of the afternoon, I'm giving the short version of my talk there. And the title is a bit enigmatic. And if you have read my abstract, there was no abstract, so still enigmatic is. So let me spend a few slides to tell you what's all this about. So first of all, there is a subtitle that was not put online for obvious reason, which is how even abstract mathematics may sometimes be useful for your experiment. So since we are an institute for mathematics, and but we have seen a lot of things about gravitational waves and experiments and so on, I try to put together the two things. So you will judge if I succeeded or not. If you don't like this subtitle, you can use the next version of the subtitle, which is how to be roasted by both LIGO, Virgo, experimentalists and mathematicians, because I think that I'm going to disappoint both, right? So I see LIGO people will be disappointed and mathematicians as well. All right. On a serious note, let me go through the outline of the talk. I always recommend my students to do an outline of the talk. So we'll start with the beginning, there will be a middle, and then there will be the end of the talk. Okay. On a more serious note, I'm going to tell, these are the words that you will hear in this talk. GPU, Hausdorff, unsupervised, Julia topological outlier, thermalization, popcorn, number, Brownian, and cauliflower. There is a thread on this. These are the words that you will not hear in this talk. I'm not reading them because otherwise you will hear them. All right.
Are these available in the long version?
All right. Okay. All right. So a long time ago, about 3 months ago, we started with something like this, right? We were at the beach house and we were talking about noise and LIGO and so on. So I wanted to put a couple of slides just to remind people. This is an example of the strain sensitivity, the amplitude spectral density in this case, that we see in LIGO. So I want to remind everybody once again that before we detect gravitational waves and we do amazing physics with gravitational waves, there is a lot to do to get to that point, right? And it's difficult stuff. It is difficult to, do theoretical physics. I know because I started doing theoretical physics. Oh, I cannot say that word. I started doing quantum gravity. I started doing string theory, right? So that's very difficult. Theoretical physics is very difficult. But experimental physics and data analysis is as difficult as doing theoretical physics. Sometimes, you talk to theoreticians and they say, oh, you're just to play with a little bit of code and look at the data. But as you are learning, it's not easy at all, right? The devil is in the details. In particular, in our field, the gravitational wave detection, things are very complicated because we are dealing with an extremely sensitive instrument that has a lot of noise sources. All this noise and all these components couple non-linearly, right, to give you the output of the instrument. And there is where things become complicated, right? The sensitivity, the extreme sensitivity, and the fact that the instrument is very complicated. And just as a last reminder, what we started with, this is a simplified schematics of the interferometer. Just there as a reminder how complicated are things. So when we do gravitational wave analysis and we start from the output of the detector, this is what we see every day. This is a typical day in LIGO. This was the second observing run, right? So again, there are times where the instrument is not working, and Jen is there trying frantically to make it work. There are times where it's working, but is not working optimally, at least according to the design. And then there are times where even when it's working optimally, you still have all these noise sources that accumulate in the interferometer and make your life difficult. We saw yesterday Gabi's talk, right? And there were talks before about glitches, all these glitches that are really annoying. So for example, at this time, I showed this picture before, I mean, the interferometer was working. This, I think, is Hanford, right? But there is a lot of junk there. And before we even think of doing physics and with gravitational waves, we have to take care of these things. And this is another way of showing the same thing. This, instead of spectrograms, these are glitch rates and glitches, what we heard this morning, yesterday, and so on. So you see that at this time, there was an elevated rate of glitches and so on. So now, how do you address this? We have seen that you can address it by, well, trying to improve the instrument as much as you can. Or you can address these problems by trying to isolate these disturbances and excise them from the data, for example, or through denoising. And this is how and where machine learning, for example, is getting more and more important. We are not totally there yet, but probably that's the future. All right. Now, the simple question I have, and this question has been going on for many years. When I joined LIGO many years ago, people were already thinking about this. The question is very simple. Is there a way of characterize the noise and the noise variation in a very simple way, with one number, with one quantity, with one monitor that tells you you're good to go, or wait a second, you have to look a bit more carefully. Now, we have a lot of tools in LIGO, Virgo, and Kagra. We can look at auxiliary channels. We can look at instrumental monitors. We can do a lot of stuff, right? But then you still have to put everything together, trying to get a simple answer to this question, right? I could look at auxiliary channels, say, okay, there is this auxiliary channel that is glitching at this moment, so it means that probably I have a glitch in h of t, or there is something, sensor overflow in this moment. So, I have all these tools, but can I tell in real time, yes, I'm good to go, or no, wait, or forget this second of data? So what I would like to have is something like this. It's a traffic light, okay? Green, yellow, red. And possibly try to do this in real time. So there is a binary black hole coalescing in the sky. We get the gravitational wave. The gravitational wave enters the instrument. And can I tell a second later, even when I'm detecting that, okay, in this moment, my noise is okay, right? So the parameter estimation that I get in low latency, or the sky map that I get in low latency, is reasonably good. Or wait a second, in the past 3 minutes, there was something happening in the interferometer. Okay, so, and I want to do this in a totally unsupervised way, right? So forget about machine learning I cannot say the word, right? I want to do it unsupervised, right? This is the ultimate artificial intelligence that we want to implement. Now, do I have the answer for that? Probably not. But I want to show you maybe something that may have some potential. All right. So before we go there, let me spend a few words about the process, right? So this is what was happening in 03 and will likely happen again in 04 in the next science runs. We keep improving, but the procedure will be essentially the same. So we have automated ways of producing the triggers and looking at the data and so on. Ultimately, all this goes to humans who have to decide if the data quality was okay, if there was anything suspicious, and then provide all these probabilities of, for example, the trigger to be terrestrial in origin or astrophysical in origin, and until we get out to send the notice, right? So there is a lot that goes on in this process. And if you are in LIGO and Virgo and you have access to all these logs of the rapid response team and so on, you see that people go online, they call each other, they put log comments, they look at spectrograms, they look at Q-scans, they look at data and so on. And at the end, you have your beautiful comment, okay, H1 and L1 both look clean around the time of the event. There is a little bit of noise, but I don't think that will cause any problems. So, okay, let's go, let's send this notice, right? And we're getting better and better, right? So at the beginning of the first detections, they were maybe took an hour to do this. Now we can do it in 5 minutes, 10 minutes, right? Still, there is some heavy stuff involved. And for example, these are the metrics that the rapid response team had to use during 03, right, to vet the candidates essentially on the fly. And you see there are a lot of questions here, right? Was the time suspicious? There was a glitch there. There was noise. How was the noise? There were auxiliary channels active. Was the detector in a nominal state and so on, right? There are a lot of questions that you need to answer and not only one. So we are very far away, or maybe we are just far away from having a traffic light that tells you green, yellow, or red. In particular, what I want to focus on is this question here, which in a certain sense encompasses all other questions, right? Was the detector in a nominal state? So was it working nicely at that point? Okay, and I want to do it possibly with a method that can complement all these methods, and at least in low latency gives you an answer right away, right? Without going through all these things. So something that can tell you if the noise was stationary, something that tells you if maybe auxiliary channels were glitching or not, and so on. All right. So what I want to do, and this is my goal, and again, I don't know if I'm succeeding, but at least I try, is to build a nominal metric that tells me if the interferometer is operating in a nominal state, starting from just the strain or any of the auxiliary channels, possibly just from the strain. So I want to go from a time series like this to my traffic light. And can I do it in low latency? Okay, very ambitious. All right, so how do I do it? Or maybe how can I try? Well, sometimes you have to think out of the counting box, right? So I was thinking, I've been hearing about fractals for a long, long time. I remember many years ago, there was this debate about large-scale structures and CMB, if the large-scale structure of the universe is fractal or not, and so on, right? Also, the fractal idea, due to essentially formalized by Mandelbrot, had its origin on noise, in noise studies. So Mandelbrot was actually employed at IBM in 1961, and he was charged to try to characterize the noise on transmission lines, right? And then what he noticed is that the more he was zooming in on the noise of these transmission lines, the characteristics of the noise were not changing, right? So we would say that it was a scale invariant problem. And so he was a smart guy, so he got the idea of connecting it to fractals, right? So what I'm trying to do today is to try to use the fractal idea to characterize the noise of gravitational wave interferometers. If you're thinking that I'm crazy, that's possible, and this would be a right time to leave, okay? All right. Okay, so if I'm crazy, I'm not the only one, because fractals have been used in all branches of science, from chemistry to biology and whatever, right? And even a few months ago, on the Science cover on the cover of Science, okay, there was a fractal. There was an article on fractal. You see, this is a cauliflower. Okay. So the idea is not new, but as far as I know, nobody has tried to use it to characterize noise in LIGO and Virgo. All right, and now a pretty picture, the Julia set, okay? So this is a fractal. It's 20 lines of Python code, 30 lines of Python code. And it's just there because it's pretty, but also because it shows you in a pictorial way what's the idea of the fractal. So the fractal is a structure, right, that is self-repeating, is scale invariant. And as such, it has what we call a dimension, which is not an integer dimension. And this dimension can be used to characterize the complexity of the set. So this movie at a certain point ends because computers are finite. I cannot run this forever, right? But you see that the complexity of the picture is increasing with time. And if I could zoom in, I will see the repeating stuff. So this object actually doesn't have, can be drawn on a two-dimensional surface, but doesn't have dimension equal to 2, okay? All right. Now, let me spend just a few words. I won't go into details about the math of the fractals and how do we define the fractal dimension, which is what I'm going to use to characterize the noise of the detector. All right, so first of all, we have to introduce the notion of a space, of a topological space. And for the mathematicians in the audience, this is the definition of a topological set, right? And so if you have a set, and for example, a set of points, and then you can, this defines a topological space, and you can define the dimension of this topological set, for example, using this procedure. There are different ways of defining the dimension, the topological dimension of a set and the fractal dimension. This is just one example, which is, I think, intuitive, right? So you have a set, right? And you try to, you cover it, right, with objects. And then at a certain point, you find that you can cover completely this set, at most with n plus 1 of these coverings. I'll show you a picture in a moment. That defines the topological dimension of the space, which is that n. So for example, if you take a circle, and, oh, I have a pointer. Okay, if you take a circle like this, and you draw it in a two-dimensional space, and then you cover it with patches, right, in this space. So these are these color patches here. And then I do a refinement, okay? So I shrink them as much as I can. And remember that these are open sets, right? So I can shrink them as much as I can on this circle, but due to the fact that they are open sets, they will have to overlap in a region, right? So the maximum number, the minimum number of open sets that I can use to cover these at a single point is 2, right? So they have to overlap. So the dimension of a circle is 1. If you try to do it with a disk or a square like this, and you try to cover it, you find that for any point of your space, you need to have 3 of these open sets overlapping, right? So the dimension of this disk is 2. If you try to go lower, so have only 2 patches overlapping, you will leave some of these points out, okay? So this is the Lebesgue covering and allows you to define the dimension of a set. In this case, is the set of points of the circle of that square there. And in general, you can prove that if you have an n-dimensional Euclidean space, right, the topological dimension is n. Okay. Now, fractals are objects with a topological dimension that is not integer, right? And the definition is here, right? So a fractal is a subset of an Euclidean space with a fractal dimension that strictly exceeds its topological dimension, right? And you can give a definition of the fractal dimension here as again, the number of covering areas that you need to cover that your set. So for example, if you try to cover the Julia set that I showed before, you find out that the number of coverings you cannot do with 3. You can do it with 3. You cannot do it with 2. So the fractal dimension has to be something between 2 and 3. So the fractal dimension of that object exceeds the topological dimension that would be the dimension of the plane where you put it. Okay. And there are different ways of defining this. One is the box counting, right? So you try, which is what we were saying before. You try to cover your space with this case with balls, right, with sets. Or this, you can prove that this is equivalent, at least in most cases, if I'm not mistaken, with the Hausdorff dimension, right?
First of all, the limit, right? If the limit is actually goes to 0.
Yeah. There's a limit there. Yeah.
Maybe lim sup or something like this. And then isn't it the opposite? It's strictly less than the topological dimension. So, because
that's possible that I made a mistake. Yeah, I'll have to.
I imagine the fractal dimension is below 2, right?
Yes, that's a typo. Yeah, it has to be smaller than that. Yeah, because yeah, you will see in a moment. Yeah, and there is a limit here. Yeah, it's intended the limit for epsilon that goes to 0. This is the refinement we were talking before. Okay. Okay, and then you can prove that these dimensions, if you apply them to a Euclidean space, you get the dimension of that Euclidean space, right? Okay. So, examples of fractals. And now we are moving closer and closer to what we want to do. So, 2 examples here. One is called the Takagi-Landsberg curve, which is defined in this way. And this is a representation between, I think, 1 and -1. I'll show it to you in a moment a bit better. So this looks like a time series, so like a one-dimensional object. But if you actually compute what's the dimension of this object here, you find the dimension is non-integer. So this is a fractal object. And the dimension is a function of, this parameter, free parameter, and is given by this expression. So these are simple objects enough that you can compute the fractal dimension still analytically. Another example is the Weierstrass function defined in this way. And again, you can compute the fractal dimension analytically for this curve here. And again, you find that it's non-integer, okay? Doesn't this remind you of some noise that sometimes we see in the detectors? All right. This is the Tagachi-Landsberg curve. This is a short movie that I made, all right? And you see, just to show you that you can keep zooming as much as you want until I reach the limit, okay? But it's a self-repeating structure, and it's not a one-dimensional really series, right? You can even say, you cannot even say where actually I'm zooming it, at which point. Of course, at the end, it becomes a mess because it's sampled discretely. All right. Other two examples. Oh boy, Brownian motion and white noise. These are actually, they can be considered fractals. So the Brownian motion has a fractal dimension, which is 1.5. And the white noise is a fractal dimension. There should be also an arrow here that tend to 2, right? And you can imagine, because if you really could sample these with an infinite sample rate, you will almost fill the entire two-dimensional surface, right? So the fractal, the white noise, it can be seen as a fractal dimension in the, in the limit on an infinite sample rate, right? Okay. Now, the idea is to take LIGO noise, compute the fractal dimension, and use that as a metric to define the complexity and the nonlinearity of the detector output. All right. First of all, I need a method to do that. I cannot compute the fractal dimension exactly, right? These are data. So did a little bit of search. I found two methods that you can use to get an approximate value for the fractal dimension. Do I get exactly the fractal dimension? No. Do I care? No, because what I'm interested is in the variation of the noise, right? So if I have a systematic effect, right, that screws up my final dimension, my fractal dimension is okay, right? Because what I'm interested in is in the variation. Anyway, this is the first method, right? Is a couple of integrals, nested integrals, right? You compute these things given a time series f of x, right? We'll have to discretize these kind of things. And then after you do these integrals, it's an average of these two integrals on the interval, and then you take this limit, and you get the approximation to the final dimension. Alpha is a free parameter, so theoretically it should be independent on alpha, the final result. In practice, it's not, because we are dealing with finite series. So, but it's a free parameter. For sake of computational simplicity, for example, I fix it to 1. I checked with other value; it doesn't make too much of a difference. Okay, what the AM stands for? It's a French acronym I forgot. Okay, anyway, not important. The second method that I checked is called the variation method. This is a sort of the box counting method, but you are doing it on a time series, right? So your boxes are segments, right? So essentially you look at the variations of these segments at different scales, and then you do an average, you take the limit of this approximant, and you get the fractal dimension. The mathematical details, I think, for this kind of talk are not too important. What's important is that you get an approximation, right? So you have an estimator, and you get an approximation of your fractal dimension. So for example, if the object is really fractal, you should get the same dimension at any scale, right? In practice, that does not happen, also because your series is finitely sampled, right? So for example, you have to get the fractal dimension by doing a fit at different scales. This is an example of the fit. The slope will give you the dimension. You see that this is pretty close to a line. It's not a line, okay? But it's okay. I don't care too much about finding the exact value of the fractal dimension, but more looking at variations of this, of the dimension itself. So before we jump head on this, we have to do some tests with fake data, right? Okay, so I took a few fractal curves for which we know the theoretical dimension, and then I check my methods, right? And two things to take out from these slides. First of all is that you can get the right value with plus or minus a few %, which is not too bad, in a reasonable time, a computational time. And the second important thing is that between the two methods, right, this method is much slower than the other one because here I have to do 3 nested integrals and so on. So, however, it's a bit more accurate. In the future, when I'll become smart and will be able to program decently, I might want to use this one, right, if I'm able to make it fast. But for the moment, I'm using this one. It's a bit less accurate, but it's faster. However, you see that the difference is, you know, a few %, something like that. All right. Second test. So we saw both Brownian motion and white noise, right? So this is white noise. Should be 2 or very close to 2, right? And this is 100, run, since white noise is stochastic, right? It's random noise. I do it 100 times, then I fit to get the mean. I'm pretty close to 2. This is good enough for me. And then we can repeat the thing for Brownian noise, and this should be close to 1.5. And it's 1.44, 1.46. And if I decimate a little bit less, or if I, play tricks, I can get even closer, right? But I don't want to wait there for days to get the result. So good enough. All right. And now we're ready to apply to LIGO data. This is 402 because I didn't have time to put the pictures 403. So sorry for that. Anyway, O2 is good enough. This is LIGO Hanford, right? This is for the open science data, so I can show them to you here. And this is the fractal dimension of one of the LIGO frames, so 4,096 seconds. Each dot is the fractal dimension of 1 second of data, right? Sampling rate is 4,096 hertz, and then I decimate a little bit. I do a small approximation to the equations we saw before. So, first of all, LIGO noise is fractal. This is a time series, but the dimension is not 1. You see at this time, it was around 1.3, right? This is interesting just by itself, right? Who knew that the LIGO noise is a fractal set, okay? Also, this is a quiet time in the interferometer. So I took this hour and 20 minutes of quiet time. You see that the fractal dimension is essentially stable. It fluctuates a little bit. Remember that there are also, numerical approximations and so on. But is generally stable, at least in 1 hour. Except there are some times where this fractal dimension goes a little bit off, right? And remember, these are 1 second of data, right? So for example, at this second here, the fractal dimension was, well, higher. Probably this is a 2 sigma higher or something like that than what I'm expecting. What are these things? Glitches. These are glitches, okay? So every time the interferometer glitches, it changes the structure of the noise, becomes either more complex or more simple, okay? Changes the fractal dimension that is a measure of the complexity of the noise at that point. So I can use, in principle, this simple measurement to check if there is a glitch or not, if the interferometer is behaving properly. Now, what is behaving properly? Well, in this case, is this average there, right? So suppose you are monitoring this continuously, and at a certain point, you have a candidate detection. I can look at what's happened before and see relatively easy, immediately, right? I do a fit if the noise was stable in the delta t time before that detection, okay? Now, sometimes the fractal dimension changes. For example, here the fractal dimension is changing on time scales of 1 hour. So you still see that there are glitches, right, short-term glitches, but this obviously is telling you that the nature of the noise was changing during this time. Why? Well, I don't know. I had to do a little bit of follow-up if I want to learn why, right? It could be, I don't know, maybe there was microseismic activity, or Jenny was doing something to the Hanford interferometer, turning on a line or doing something like that. But what matters here is that the noise is changing. Sometimes it changes so much because things go completely bananas that you lose lock. Here the interferometer loses lock. See what happens to the noise, right, just before it loses lock. We are moving from a fractal dimension, which is 1.3, what we could define as nominal, to something that is, this is probably 5, 3, 4, 5 sigma, something like that, right? Look, here there was, I think this was probably a time where it was just on a high noise, I didn't lose lock, right? But look, I can I can tell that something will not go too well quite before, right? Because the noise starts changing characteristics. Okay, so, and in particular here, you see that these were later identified as, Cat1 glitches and so on. And these are the glitches that lead to lock loss. And if you count the number of points, 1, 2, 3, 4, 5, 6, 7, right? About 7 seconds before I lose lock, things start changing. This is an example where the interferometer didn't lose lock. This was just in a high noise. I know because then I went to do some follow-up to understand what's happening, right? So you see the fractal dimension was stable before and after. I don't know what happens here because I'm using O2 data, but if I go and look at the internal data, I'll still have a fractal dimension here. Probably will be all over, right? Because something is happening. So similar noise before and after is an indication that the thing is still stable. There is only a sort of transient that happens there. This is an example of how the fractal dimension changes when we regain lock, right? So look at this. It's going again at 1.3, right? But it ramps up, right? First of all, the dispersion here is much larger. So it means that things here were varying much more on a time scale of 1 second. But also there was a variation which is about, what is that, 1,000 seconds? What are 1,000 seconds? I don't know, 30 minutes, 1 hour, something like that. Now, my postdoc who is a Hanford says, oh, I know what's that. It's the thermalization of the mirrors, right? We had to wait for an hour or something like that for things to settle down. I can actually see that with the fractal dimension. Right, this I've already said. Okay. Now, interesting, the noise, even when it's stable, is not the same across the run. So this was December 8, and this after 3 months, right? You see that they are both stable, but with a very different dimension. Why? Because probably there was some commissioning in between. The configuration was changed. There was a buffer installed that took your scatter light or something like that, right? So I can really, with this, I can really measure the characteristics of the noise. And I can even see when things are happening, right? So this was stable and then was taken out of lock, and then it regained lock again. This is, I think, the same thermalization, and go back to nominal configuration, which is different than the configuration that was before. But what's important is that this is, we heard, I think, about causality, right, in machine learning and so on. I don't need to know what's happened next, right, to characterize the noise in this way, because second by second, I can get a measure of how the noise is changing. This is actually, I went to see what happens to that day, and this change here, if you, let's see, there is what I was able to trace that. There is that line that is changing, right, exactly at that time. And probably the presence of that line is changing the complexity of the noise, and I can record. Okay, now, since we heard a lot about glitches, let's talk a little bit about glitches. Look at this. These are huge glitches here, right? So what can I say about those? So let's do a little bit of follow-up, right? So first of all, let's isolate those points, right? There are several ways of doing it. This is the most stupid one, which is the one I can think about. Okay. No laugh at this. Okay. So I simply took that 4,096 seconds, take the average, and look at deviations above 2.5 sigma. Okay. All the stars are the points where the fractal dimension is changing, right? And then I go and do some spectrograms, Q-scans, look at some stuff. Lo and behold, look at this. For example, this here, 1, 2, 3, 4, 5, 6, right? So I'm expecting something along 6 seconds, right? This is one of them. You see that there is all that noise there. Zoom a little bit out. Now this is 4 seconds. See, this is a Q-scan of those 4 seconds, right? So really, this is a huge glitch, right? So it's changing this fractal dimension a lot. This is another glitch, like this. This is spectrogram, okay? So 1, 2, 3, 4, 5 seconds. I'm expecting something on the order of 5 seconds. There it is, right? And then this is the Q-scan, if you prefer it to see. So these are really glitches, right? Now, the idea here, since we're talking about machine learning, is to do anomaly detection, right? So I have this stream of these quantities that progress in time, and then I devise a monitor that tells me when, for example, this thing starts deviating, right? So anomaly detection. So I looked a little bit, and here I'm not an expert of these kind of things, so you guys are welcome to steal all my idea, because, by the way, this is not published. Okay. I see the guy there with the camera. Oh, no, it's online. Ah, damn it. Okay, it's not published, but anyway. So this is where, I mean, people like you can really be useful, because I don't know these kind of things. But I looked, for example, at the local outlier factor method, right, to identify these anomalies. The only constraints I want is that it's unsupervised, right? And, you know, I don't want to, you know, I cannot say the word, but I don't want to use those machine learning methods that require, okay, I want it unsupervised. Damn it. I'll end up saying the word. Okay, so for example, this is an example. Recently, also there was a paper by Julian Dean, Jess McIver, and so on about I think it's a similar idea to they don't use fractals, but to identify glitches using one of these methods, the temporal outlier factors, and so on. So, for example, this is glitch identification with LOF. So what I do is I compute a rolling mean, right, of this stream of data as they come, right? And then I use the local outlier factor method to identify when there are anomalies. And you can see that it's actually complicated because you have to take into account long-term variations, short-term variations. It's not as easy at all. But okay, at least in this example, right, those days, so I can identify relatively well, the anomalies. In my opinion, that's an anomaly too, but I miss it because this glitch is so loud that the rolling average is affected and so on. I can also identify other anomalies, right? And those anomalies are due to the fact that, the absolute value of the fractal dimension may remain the same, but there may be huge jumps, right, between second by second of this fractal dimension. So maybe then the previous point is there, the next point is there, so this is interpreted as an anomaly. Yes? Look at the clock. Okay, all right, so quickly, anyway, glitches, right? So if I use a more refined method, I can also identify glitches that are less loud than what I was showing before. So there is some potential in it. For example, that's a glitch that shows a line here. It's not too evident, but it's there. Okay, long-term noise variations, we already talked about that. So for example, if you look at this hour of data and you ask yourself what's happening, right? Do you remember I told you there was that line and so on? You see that the line itself is changing. Here you have a lot of sidebands, right? And then that becomes clean enough. I think that's the cause for this. And maybe Jenny or people who know more about the detector can correct me. All right, and now, just to wrap up the movie, the popcorn, all right? So I'll show you about, if I'm not mistaken, is 2 days of data. It's accelerator, right? We don't have to say. And then I'll cut it off. See how the fractal dimension changes with time. Yesterday we heard a talk about scattered light glitches. So I took us 1 day, 1 or 2 days of data, where at the beginning there is not much scattered light, and then the scattered lights start picking up because there is this microseismic noise, until it becomes so bad that the interferometer goes out of lock, and then you'll see it going out of lock and recovering. Okay, there it is. So here is still relatively quiet. There are already a lot of glitches, right? That's already scattered light, but not as dramatic. And then if we wait a little bit, right, we'll see that the scattered light starts picking up and becomes really bad, okay? Now, this is really bad, and at a certain point, the interferometer goes out of lock. And 1, 2, 3, not yet. Okay, there it is, right? And then it takes some time. I have no data in the strain channel, and then try to lock it again, and then there you go. You are back in business, right? With a little bit of glitches, but most of the scatter light has gone. All right, so conclusions before the chair of the session kicks me out. This is a very simple algorithm, right? I run it on 1 GPU at Caltech, right? I implemented Numba, and I can process 1 second of data, h of t data, in about half a second, including input and output. So this thing can run live, right? And if instead of a GPU, I have 10 GPUs, I can run these on 10 different channels, right? So I don't need to run this on H of t. I can run, if I have a very good witness channel or something like that, I can run it on that channel, and I can identify if something goes wrong right away. Indeed, I was able to process about a third of O2 open data in a few days, in a week, 10 days, or something like that, right? So a little fractal dimension, a little bit of machine learning for anomaly identification, and I think I can characterize the noise on the interferometer in real time. Now, if this is going to be useful, I don't know. I hope so, okay? But at least it's something to think about that can be easily implemented in the summary pages or as a monitor, and then if it's good, it's good. If it's not, we'll throw it away. Thank you very much.